Bertossi. Leo is a professor at the Adolfo Ibanez University, and he's an emeritus of University of Carleton in Canada. And also he has been working with the relational AI company over the past few years. Now, Leo has made the very basic, very fundamental contributions to the database theory, particularly the theory of database logic, dependencies, consistency, inconsistency, and maybe to me most importantly, the theory of data quality. Okay, and over the past years, he has been working on connecting between database foundations and aspects of artificial intelligence, in particular aspects of explanations and responsibility of, in general, in machine learning and artificial intelligence. And we have been working together jointly on how to measure the contribution of tuples to query answers. Maybe Leo will say something about that. And that's it. So Leo, thank you very much for being with us today and giving this tutorial. Just a technical question regarding questions that arise. I thought that if anyone has questions, they can write it on the chat. And Leo, if you have the time, if it works for you, then maybe you can look at the questions, or I can look at the questions from time to time and see if there's anything that you want to answer. But do remember that we have the discussion session later, and Leo will be in one of the rooms, and then you can get in, relax, comfortably ask whatever you want. So we, you'll get the chance to ask the questions. That's it. Leo, the stage is yours.
Okay, can you see my slides?
Yeah, okay. I can see it very well.
That's great. Okay, well, hello everyone. I'm very happy to be here today. I mean, presenting on this subject in which I have been working for the last, let's say, couple of years or so. I'm also grateful to the organizer for having invited me to give this tutorial. I mean, this is it's very nice of you that you did that. And actually, it's very nice, even more important, that you are keeping this event and this community alive and communicated. I mean, that's great. That's very important. I think the Alberto Mendelzon workshop has had an impact in Latin America, in the community, and also beyond Latin America. It is a well-established, I mean, event. I mean, that suddenly, I mean, unfortunately, it was interrupted due to the COVID-19 situation, but we hope to have it back, I mean, as before. Okay, thanks again for the invitation. I'm going to present on explanations in data management and artificial intelligence. I apologize to some of you who may have heard, I mean, part of this talk and some other, I mean, events, or but I mean, I see from the list of participants that, well, there are many people who seem to be new. I mean, so that's good. I mean, okay, so I have been working, I mean, actually, since I finished my PhD, actually, I started working in artificial intelligence, and then I started moving to data management. So artificial intelligence has been always in my heart, and have always been doing a bit of research, I mean, and also in combination with data management. So it is, I'm very happy to see two areas which I love converging in some sense. So I hope to convey what I'm trying to suggest. Okay, what's going on here? Okay, let me start with a very simple example. I mean, just to show the gist of what we can do in databases, among many other things. So we have here the database, very simple one. I mean, of course, you can think that this could be a huge database with a lot of data, so things are not as easy to understand as when you look at this particular couple of tables. So I'm just thinking those terms. So the queries, are there pairs of official stores in a receiving relationship? I mean, the second table here, store, is supposed to store the official stores. And here there are other stores that have some sort of relationship in terms of shipping goods and receiving them and so on. So basically we have to combine the two tables. And actually this is a query, right, that we can express in logic as usual, right? I mean, so basically we have to do a join between the receives and the store table on the left-hand side, on the right-hand side. Well, it doesn't matter the order, but I mean, important thing that the store had to be official, both participating here, right? And so this query, in this case, in this database, it is true because this join that we have here expressed as a conjunction of atoms. There is a join because we have repeated variables, right? So it's the usual join in SQL. So the query is true in the database, and then it is a Boolean conjunctive query. It is a conjunctive query, a conjunction of atoms. And also we have here existential quantifier. So basically it's a closed query, it's a sentence that is true or false in the database. Yeah. So the question is, what tuples cause the query to be true? Yeah. What are the tuples underneath that make this query true, that all we are observing is the query being true, right? So, and then we can ask a bit more. I mean, how strong are those tuples that help to make the query true? How strong are they as causes? How strong is a quantitative question here. So we would expect tuples like receive S3, S3, and receive S4, S3 to be causes because they participate in the join, because I can do the join of this tuple with this on this side and with this on the other side. So here. So basically this, we expect them to be causes in the intuitive sense. And the idea is to, of course, to formalize the notion a bit more. Yeah, explanations for a query result. That is what we are asking for. Of course, we can extend this kind of questions, I mean, to other problems like what are the explanations or the causes for a constraint, a semantic constraint to be false in the database, and other data phenomena for which we want to find some sort of explanation, right? So here the core is of the situation is to find explanation that in this case I am casting as causal explanations. Okay. So a database should be able to provide explanation together with the answers. I mean, and the aim here of the whole enterprise is to model, specify, and compute causality. Yeah, and a large part of our research is motivated by trying to understand causality in data management from different perspectives. Yeah. So in particular, we have connected this problem in database with problems in AI, but I will probably say a bit more about this. Let's change scenario. Now we are in the context of, let's say, machine learning, classification models that have been learned from training data. So this bank has a classifier, is a system, as an algorithm that actually for most of the people in the bank, if not for all of them, is a black box that help them to decide if to grant a loan or not. So we have an entity that is basically here is basically represents a particular client who is applying for a loan and has some feature values. I mean, the name, the age, the occupation, the salary, the neighborhood where he or she lives, and then this entity goes into the classifier. It is understood that it is about a loan, I mean, a request, and the classifier answers no. Okay, very, very disappointing for the loan applicant. And then, of course, the loan applicant, especially in these days, where people are extremely sensitive about everything, right? I mean, the applicant wants an explanation, right? So, so the question is, which are the feature values here in this record that are most relevant for the classification outcome, in this case, for having received the label no? Yeah. And then we can be a bit more specific. What is the contribution of each of these particular feature values, I mean, to the outcome, in this case, the negative label? Okay. So in the spirit, at a very high level, it's not that different from what I was asking in the context of databases. Yeah. So the questions like these are at the very core of what is quite fashionable in these days, that is explainable AI. Of course, it's a whole area of research that is quite effervescent in these days. There is a lot of things to do, many things to do, and I hope we will have time later on to discuss about research directions. Causality as such has been, well, of course, causality, the idea of causality can be traced back to, I mean, to I don't know, I mean, Hume, Locke, if not earlier, right? I mean, the idea of causality is kind of somehow, I mean, belongs to the human spirit. So, but in AI, I mean, people started formalizing causality, let's say about 3 decades ago or a bit more. And in particular, one area of causality as found in AI is actual causality, and that is the subject, let's say, I'm going to consider. Actually, as a part of actual causality, you find also a quantitative notion of responsibility. You can guess that is related to the question that we were asking before, is a measure of causal contribution, right? Something can be a cause and contribute, I mean, to a certain degree, I mean, right? So this causality and actual causality, they are based on counterfactual interventions. You are going to see some of them along the presentation. What are counterfactual interventions? I mean, we can say, I mean, in intuitive, informal terms, that basically they are hypothetical changes in values in a causal model. So we usually have a causal model that is very explicit or sometimes implicit, yeah, and we start playing with values or items in this model to detect other changes, and that allows us to possibly perceive potential causes for things that happen, right? So basically, we have questions of the form. I mean, what would happen if we change this? I mean, would something else change or not? So by doing so, we can identify actual causes, right? At least it's from a heuristic reasoning that has to be sanctioned through a formal definition and model, right? So in this case, in the case that of the classification model, I mean, I can ask, do changes of feature values, I mean, for this particular entity or client, changes would make the label change from no to yes. That would be a natural exercise to perform. So this is the idea, this is the gist. So we have investigated causality and responsibility in data management and classification. We have considered semantics, computational mechanism, intrinsic complexity, logic-based specification, reasoning with those specification of causal causes for phenomena that we observe. And when I say we, I mean, I'm thinking of several co-authors, not necessarily always the same. At the end of my presentation, I have citations to the work, I mean, I have been doing with the collaborators. So I'm not going to mention many people along this presentation, so nobody should feel offended by that. At the end, you will find a list of references. So when I say we, I'm talking about possibly different collaborators, not always the same. Yeah, only a bit part of this research has been done by myself, yes, alone on my own. Of course, there are other explanation scores. In the literature machine learning community, they are usually called attribution scores. So we want to attribute, I mean, a score a certain degree of relevance with respect to something that we are observing. And some of them have been applied in data management and machine learning, and in both areas. Yeah? We have, for example, apart from causality, we have the causal effect score that we introduce and use in a paper. I'm going to say a bit about that, not too much. The Shapley value has become quite relevant, and of course, responsibility, as I said before. So we have research on them, I mean, all of them, and I'm going to present a bit of this around this scores, I mean, in the rest of the presentation. We also want to specify counterfactual interventions. I mean, yeah, logically, I mean, specifying counterfactual explanation and hopefully reasoning about them. Hopefully, I will have time to reach that point in my presentation when I talk a bit about reasoning, because that is also very important. And we want to also compute responsibility score from specifications. I mean, use the specification to compute the scores. So this is the plan for the tutorial. Really, maybe very ambitious, but I want to leave with you the slides in case I can't cover what I was planning to cover. So I'm going to talk about different scores in databases and also in classification in machine learning. And if I have time, I hope I can reach this part where I will tell you about counterfactual intervention programs that have to do with these declarative specifications. And I should finish with some final remarks, but I will also leave them for the discussion. So this is not very important to reach this point. If you want more details about all of this, I have this paper here that is going to appear soon as a part of the Reasoning Web School. I mean, so it's a 40-page paper, so it contains much more than I have here in these slides. Okay, let me say a few things about causality in databases. So it is about causality-based explanation for query result. I mean, of course, it is based on actual causality as developed by Judah Pearl, Joe Halpern, but basically Alexandra Meliu, Dan Suchu, Wolfgang Gatter-Bauer. I mean, they in BLDB 2010, they started using it in the context of databases. So we have a relational database and a Boolean conjunctive query like the one I had before. And then this is the query queue, and then a tuple in the database is called the counterfactual cause. A counterfactual cause for the query to be true in the database. We are assuming the database satisfies the query. When, if I delete the tuple from the database, the query is no longer true. Obviously, this shows that tau, the tuple tau, is really relevant. I mean, crucial for making the query true. So that is the ideal cause that we could find. But there are other situations where deleting one tuple, only one tuple from the database is not enough to invalidate the query. So we have to generalize, relax a bit this condition. So a tuple now is an actual cause, the difference with counterfactual, if it needs some company to invalidate the query. That is the idea. Even if you don't understand or you are not interested in what I'm going to formalize here, this is the idea. It needs some company. So it's an actual cause for the query to be true if there is a contingency set, the set of companion tuples, gamma, a subset of the database, such that tau is a counterfactual cause, I mean, in the same sense as before, but not on the for the original database, but the database from which we have removed the tuples in this companion set. Yeah. So basically it's saying tau needs company to invalidate the query. Yeah. And this notion has been formalized in the context of actual causality by Halpern and Pearl. And this is the conference paper. This is the journal paper. Yeah. So now we want to measure the responsibility of the cause. Actually, obviously, if tau is a counterfactual cause, it's really responsible for the query to be true, right? Actual causes may see their responsibilities diluted due to the company, and of course, the responsibility is going to be related with the size of this companion set. Yeah, and that is basically what the notion captures. So the responsibility of an actual cause tau for a query is 1 divided by the cardinality of the smallest in size, I mean, subset of the database that is a contingency set for the cause tau plus 1. Yeah. So in the case where this guy doesn't need any company, this is going to be the empty set is going to be 0. So the responsibility is going to be 1, but it's the maximum responsibility. Otherwise, the responsibility will be between 0 and 1. Yeah. And if a tuple has nothing to do with the query, basically we get the 0 responsibility. So we are usually waiting to find, I mean, high responsibility tuples because they provide more interesting explanations. Actually, the notion of responsibility is based to Chocolate and Halpern in a paper in 2004. It's not explicitly, at least in the paper by authors. Okay, so let's illustrate this very quickly. We have a database with relation R and S. This is the query, as before, more or less, yeah, basically the same idea. And then what are the costs for Q to be true? Well, S3, SA3, that is this one over here. If I delete this tuple, actually there is no way I can make the query true. So in this case, we have a counterfactual cost. It is good enough to remove this tuple to invalidate the query. So the responsibility, as I said before, is 1. Now there are other tuples, R A4, A3, is one over here. It's an actual cost for Q, and it needs a contingency set. If I delete this tuple, then the query is still true. So I need to remove, in addition to this tuple, also this other one, for example. So this becomes a contingency set for this actual cost, and then obviously the responsibility is going to be 1 over 1 plus 1, 1/2. So this is what I just said. So the responsibility is 1/2, because 1 is the size of the smallest contingency set that we can find for this particular tuple over here. Yeah. The same, I mean, for the same reason, I mean, these are other actual costs with responsibility 1/2. Yeah. This is the idea. Yeah. There are many computational problems around this notion of causality. The notion is not very difficult, but of course you want to compute causes, you want to decide if a tuple is a cause, you want to know, compute the responsibility of a cause, you want to know if a tuple has a maximum responsibility, you want to know if the responsibility is above a certain threshold. I mean, many computational problems appear. Some of them were investigated in the paper by Suchu, Meliu, Gatterbauer. Yeah, and this is so computing causes, deciding tuples, compute responsibility, computing most responsible causes. That is but the problem that is obviously interesting. Deciding if a tuple has responsibility above a certain threshold. So the complexity for conjunctive queries and union of conjunctive queries is by now more or less clear. Some of the results, as I said, were obtained by the original paper. Some others were obtained by Babak, Saliming, and myself in a paper. And these results that we obtained in relation to responsibility, actually they were obtained via a connection between something that was at that point a bit unexpected. I mean, causality and database repairs. Yeah. Actually, this connection has been quite fruitful and useful. Yeah, and also we have combined causality and consistency-based diagnosis that has to do with diagnosis as found in AI, and that is actually that goes back to, I mean, papers in the 80s, the late 80s or early 90s. By Ray Reiter, etc. Actually, this was also very nice. I think a very nice, I mean, connection that was unveiled and was exploded. That is most important. I mean, right? So let me say a few things very quickly about the database repairs. It is something that we introduced in a POTS paper in '99 with Marcelo Arenas and Jan Chomsky. So the idea is simple to introduce by means of an example. I mean, there are many computational problems that are not necessarily easy. But we have a database that does not satisfy a certain set of integrity constraints. Think of functional dependencies or denial constraints. These are denial constraints. For example, this is saying, I don't want to find in the database, I mean, this join to be true. Yeah. Basically, these denial constraints are prohibitions of certain joins. I don't want to satisfy this join in the database. I don't want to satisfy this join. This is not, there shouldn't be any values for the arguments in the predicates such that this join becomes true, or this one. So it's a prohibition, right? So of course, this is one class of constraints, and we could also consider functional dependencies and key constraints as a form of denial constraints as well, okay? There are prohibitions of a certain combination of things. So we have a database that fails to satisfy the intended constraints, and then what do we do? That was the question that we posed in this paper. Well, what we do is basically consider all the possible repairs of the original database. The notion of repairs can from different possible semantics. I mean, but basically we have a collection of possible worlds. Keep that in mind. They are instances of the same schema as this database, but they are consistent. They do satisfy the constraints, and they minimally depart from the original database. Yeah. So there are some repair actions performed here that lead to this collection of possible repairs. Yeah. Consistent versions of this database. And we can pose the query to this collection as a possible, in the sense of the possible world semantics. I mean, and the consistent answers to the query Q are going to be the answers that we can collect from all the possible repairs simultaneously. Yeah. So these are the semantically correct answers to the original query. We don't want to query directly the inconsiderate database because we can get things that do not make sense with respect to the intended constraints. Yeah. So this is the idea that there was a task. In this case, this table violates these constraints, and we have to repair. And we are going to choose a particular repair semantics that is based on deleting database tuples. I mean, when you have denied constraints, only deletion of tuples or changes of attribute values can help you restore consistency. So let's go for deletion, tuple deletion. In the paper that I mentioned before, you can find a version with changing attribute values. I'm not going to say anything about this here today. Okay, subset repairs. I mean, these are two subset repairs. These are basically two subsets of this database or two sub-instances, but they now are consistent with respect to this constraint. They do satisfy the constraints. And here you see these two are perfectly admissible, although this one looks closer to the original database in the sense of the size. Here we have 4 tuples, here we have 3. Here we kept only 2. However, they are incompatible with respect to set inclusion. This is not included here, this is not included here. So under the subset repair semantics, we keep the 2 of them. But if we can also go for the cardinality repair semantics, that basically would keep only this one because it differs from the original database by only 1 tuple. Yeah, and the 2 of them are useful, but actually for causality purposes, the C repairs turn out to be particularly useful, and they have been less investigated than the subset repairs. Yeah. So these are maximal cardinality consistent subinstances. These are maximal consistent subinstances. This is with respect to set inclusion. This is with respect to cardinality of deletions. Yeah. Okay. Now, what is the connection between these repairs that have initially nothing to do with causality and causality? Well, basically, the idea is not that difficult once you see the connection. I mean, you start seeing the connection. Yeah, developing the details is not that complicated. So we can start with a Boolean query as before. We want to find the causes for this tuple to be true in a particular database. What do? We obtain the actual causes and contingency set from database repairs. So all we have to do is reduce this problem to the problem of dealing with database repairs. Yeah. So the negation of this query is basically a denial constraint. But this query is saying, give me values, or are there values for these variables here that make this join true? Then you consider the negation. The negation is logically equivalent to this denial constraint. It's a prohibition of a join. Yeah. So then you are in a causal situation. So the query original holds in D if and only if the database is inconsistent with respect to the associated denial constraint associated to the query, because it's asking for things that make this true, and it's saying there shouldn't be anything that makes this true. So obviously the database is inconsistent if the query is true in the database. So then you can start working with repairs and not directly with causes. Yeah? So the S repairs are associated to causes and minimal contingency sets. Yeah? And the C repairs on this side are associated to causes, of course, minimum contingency sets, and maximum responsibilities. Yeah? So basically, the characterization is as follows: a database tuple is an actual cost with subset minimal contingency set gamma. Yeah, subset minimal contingency set gamma. If and only if I remove gamma together with tau from the database, I obtain an S repair, a subset repair, in which case I can read the responsibility from this gamma is 1 over 1 plus gamma. Yeah, and now this is the most important part. I mean, the connection with cardinality repairs. Tau is an actual cost with minimum cardinality contingency set gamma, if and only if the same happens, but now the difference between D and gamma together with tau is a cardinality repair. And in this case, the tau becomes also a maximum responsibility actual cost. And this is the problem in which we were interested. I mean, computational problem in which we were interested, among other things. Yeah. So exploiting the connection, basically, what is important here, it was known that deciding and computing actual costs for conjunctive queries could be done in polynomial time in data, in the size of a database. In the paper by Melio, we extended this to union of conjunctive queries in this paper with Babak Salimi. And as I said, most computational problems are related to repairs, in particular cardinality repairs are probably hard. And then we have a paper in ICDT 07 that were investigated cardinality repairs, several computational problems, and we basically leverage these results to obtain results for causality. So this is important. So for example, one of the problem is the responsibility problem. Deciding if a tuple has responsibility above a third time threshold turns out to be NP complete for union of conjunctive queries, just to give some of the results. Or computing the responsibility of a tuple, is complete for this class for Boolean conjunctive queries. What is this? This is the functional version of the responsibility problem, right? It's not a decision problem, it's a functional. I want to compute the responsibilities. That's why we have an F here. And then polynomial time. You see, that's great. Polynomial time, that's good. But, well, not that good because actually polynomial time, but we are allowed to make a logarithmic number, which is not very, very large. I mean, in comparison with this, with n, a logarithmic number of calls to an oracle in NP. Well, that is more than polynomial, of course. We could, for example, call a SAT oracle, right, for satisfaction of propositional form. So basically, and this is complete for the class. So this is saying this problem is hard, yeah, but one has to find it. And now deciding if a tuple is the most responsible cause is also now a decision problem. Well, it turns out to be complete for this class. Now it's not a functional class because it is basically a decision problem, but it's more or less of the same, basically the same complexity, right? For Boolean conjunctive query. So we obtain these results from cardinality repairs. Okay. Causal responsibility can be seen as explanation score for database tuples in relation to query results. It is not the only one. It is not the only possible score. I see that I'm going a bit slow, so I think I will. Let me just mention. I'm not going to give all the details, but this the motivation. Here we have a Boolean query. Yeah. That's basically the one over here that is represented here as a data log program, but it could be represented as a union of conjunctive queries very easily. So not a big deal. We have a database represent this graph. There are connections between these nodes, right? And then the question is as to whether we can go from A to B. And of course we can, because we can do this, this, this. And then we want to see what is the responsibility of the other responsibilities of the tuples in this database. I mean, with respect to this query, is there a connection between A and B that is represented by this mini data log program? But as I said, it could be represented as a union of conjunctive query. When actually it turns out all tuples are actual causes. Yeah, every tuple in a path from A to B basically becomes an actual cost. I could remove this, the query is going to still be true because there are other paths. So I will have to remove tuples from other paths. So if I remove this, start with this one, I will have to remove this one and this one or this one and so on, yeah, to invalidate the query. So all the tuples, and actually if you compute the responsibility, all of them have the same responsibility, that is 1/3, yeah, and which is because you have to delete 2 tuples in addition to the one at hand, yeah, so that makes 1/3. Yeah, and then basically, well, you can say, well, maybe this is not very intuitive. I mean, because I mean, this one is a direct edge from A to B. Here we have a path with 3 edges. I mean, so yeah, not make. So we started thinking in a paper with Dan Suchu, He van den Broek, Babak Salini about this, and we proposed a different score, the causal effect score, in a top paper, and basically the idea is we're going to go very quick about this just to give the gist. I have the database, I have the conjunctive query. I'm not using the same example, but a simpler example. Yeah, and here this query can be expressed basically as a lineage. It's a propositional formula in the sense of propositional logic that basically for this database tells us all the ways in which we can make the query true. These X with a subindex are variables associated to the tuples in the database. And for example, I could invalidate the query by making some of these variables false and so on. Yeah. So this is the lineage of the query instantiated in the database. This represents all the ways to make the query true in this database. So this is a propositional variable. It is true in the database. This is true when the tuple belongs to the database. And we want to quantify the contribution of a tuple to the query answer. So what we did is assign probabilities in a uniform manner and independently to the tuples in the database. So from the original database that we have here, somewhere, it's the one over here, not as a table, but then we added here a column with a probability. We assume all these tuples are independent and they are equally likely. I mean, this tuple could be in the database or maybe it is not in the database, and that happens with probability 1/2. Not because you see it here, it is in the database. It could be with probability 1/2 and so on. Yeah, it's a probabilistic database. And then the X taus now become random variables because they are associated to the tuples in the database. Since the tuples can be in the database or may not be in the database, now these are random variables, but they are independently distributed random variables, and they are in the query, and these variables are Bernoulli random variables. They take the values 0 and 1. So what is the probability that Q takes a particular truth value when an intervention is done on D? So we can modify something here, and then we can see what happens with respect to the probability of the query, because now the query is not true or false, but has a probability of being true or false. Yeah. So the interventions are here. You see the intervention. I wanted to show the example for this reason. So I am using the notation that, sorry, Judah Perl uses in all his papers. I mean, the do notation. Basically, this make this variable take the value X. Yeah. And in a structural model, in this case, the structural model is basically the lineage of the query that you have here. I can say, make this variable take the value 0. That means delete the tuple of the database, or make it take the value 1, keep it in the database, and so on. Yeah. So these are, and then we can compute the queries. I mean, what is the probability that the Q is true with Y equal to 1 when I make X sub tau equal to 0? I mean, it is deleted from the database. Yeah, with all the possible combination. Yeah. And whenever I do something like this is going to change the lineage, because some of the values will disappear. And if I make X as D0, the lineage now becomes something much simpler. Yeah, it is only this conjunction. And this becomes the only way to make the query true now that I have deleted this tuple. Yeah. So this is the lineage with this tuple replaced by 0, basically. Yeah. And then I can compute. Now I have a random variable. Basically, I can compute This is the causal effect. I'm not going to compute it. I have them in the slides. I'm going to leave them for you. So the causal effect of this tuple for this particular query in this particular database is now a measure, right? It's a score. And it is defined as the difference in expected values between making the value of the query that can be true or false, right? In the case where tau is in the database, and the other case is when the tuple is not in the database. So basically, what is different between an expected value or the expected difference between having the tuple in the database and not having it, right? So this value, right, of course, a number is a number that we investigated. I mean, in that paper, here you are going to find the application. You can see this later on. What is important in the case of the original query that motivated the introduction of this score, basically what we obtain now, before we had 1/3 for each of them, now we have basically different numbers. T1 has this causal effect score, the other have this and this. This is stronger as a cause. These two are stronger as causes than these three here because they need a longer path and so on. So this is actually this is interesting per se, but also because of something I'm going to mention soon that was also something a bit unexpected for us at least. Okay.
Yeah, just one thing, like, can you aim to finish in like 10 minutes? This is the plan. Will it work? Do you need a few more minutes?
Oh, okay. I thought I had an hour, but no.
You have you have the 50 minutes, but it can we can go 5 minutes later on the expense of the.
Oh, okay. Okay. Well, let me say a few things about coalition gains and shapely values. I mean, we have this is a important thing we have been doing. So the idea is how that we have been discussing how much a database tuple contribute to the inconsistency of a database or to the violation of integrity constraints, right? So these ideas can be applied to the contribution of query results, right? I mean, as well. We started with this question at some point in a paper with Benny, who just intervened, and Stan Lipschitz, Moshe Sebak. It's a paper in 2020. So we apply this idea now to the contribution of tuples to databases. I mean, so the idea here is very simple, and I want to convey this message. I mean, several tuples together are needed to invalidate or to violate the constraints or to produce a query result. I mean, it is rarely the case that one tuple is going to be the only cause for that. You need a combination of players. And now we can take this idea of players seriously. Like players in a coalition game, some may contribute more than others. We can apply standard measures using game theory, economics, and in particular, we can use the shapely value of a tuple. Yeah, the shapely value is an established measure of contributions of a player to a coalition game. Yeah, there is an implicit counterfunctional intervention component here. What will happen if we change something that is much more implicit than in the causal approach? But let me say a bit about this. We have a set of players D. I use D just to suggest that they be the database tuples. We have a wealth distribution function or gain function G that takes set of players and send them to a real value. That is the real value associated to this team of players. There is someone waiting in the waiting room. Okay, so basically sets of players are sent to a real number. The shapely value then of a player, a particular player among the set of players, the full set of players, is going to be defined by this. It's a general formula. What I have here, I can use the instantiate it later on in different ways. Basically, what you have here is the difference. Here, S is a subset of the database of the set of players, leaving aside the player at hand for which you want to find a score. So P, the player P is left aside. You consider all the subsets of the set of players S, and then you consider what is the difference between having P in this team S and not having it, right? In terms of the gain function. That gives you a value, a number, of course. And then basically, so this is where I see something like a counterfactual game, having P versus not having it. And then you consider all the possible subsets of D. So, and then not only subset, but also all the possible permutations of the subset S. So this gives base, and then the permutation of all the tuples that follow P. So I think the picture is going to show this. Basically, what is the idea? This number here is the number of permutation of D with all players in S, this coming first, then P, and then all the others. Yeah, and then I'm reusing a picture that Esther drew some time ago. It's very nice. So you have the set of players. So far, here you have your set S, could be this, formed by these three guys. Every time you add a player, you increase this gain function. And then at some point, you start going to add this one, right? And then it goes here and produces a difference of 4. That would be the value that goes here in this difference, right? And then you consider the permutation of these players and also permutation of players that would follow after the one in green or blue, whatever color it is. I am a bit daltonic, so I have no idea, but this one, right? Yeah, and then this is the idea. Obviously, by definition, there is something like a combinatorial explosion here. That is very important to see. So the question is as to can be do better than just consider the exponential number of terms here is really relevant. Yeah. So we apply, I'm going to go faster. We apply all this, I mean, to the case of database tuples in this paper with Benny, Esther, and so on. Actually, computing the shapely value in general is sharply hard, right? This is a difficult problem. It is a difficult problem. So we can see now database tuples as players in a coalition game for the same. Well, this is the query now. Actually, this query is not chosen at random. It's a difficult query, right? It is true or false. So what is the gain function? Basically, the gain function is going to be the query itself, right? It is 1 if it is true, 0 if it is false. Yeah. So basically, the gain function is right there here in this particular case. Yeah. So basically, this is the instantiated, I mean, gain function in this case with this particular gain function that is the query itself. And basically, it quantifies the contribution of tuple tau to a query result. Yeah. Well, I already said this. It's just a Shapley value instantiated with this gain function. And we investigate algorithmic complexity and approximation problems. And actually, it is nice to find that there is a dichotomy theorem for Boolean conjunctive queries without self-joins. Actually, there's a syntactic characterization. I can see the query, syntactically analyze the query, and know it is going to be solvable. I mean, the Shapley value is going to be computable in polynomial time, or going to be sharply hard, with some extension to aggregate queries and so on. So there is an alternative notion to the Shapley value that is the Banz power index, where it's basically the same idea, but the order is ignored. That's why here you only find this term here. Basically has to do with the number of subsets of the database without considering permutations. In principle, you would think it is easy to compute, but actually it turns out to be sharply hard in general as well. And why I'm mentioning this, because, well, it is very intuitive, but actually it turned out to coincide, as we show in the paper, with the causal effect score that I introduced before, but that was something kind of unexpected. I mean, so this is interesting to mention. Explanation for classification gave me say a few things. I'm going to skip parts of the presentation, of course, but let me say a few things about the application of the Shapley value in this context. This is what I had before. What will happen here is the following. If I change here, but in this entity, the age to 25, it could be the case that I obtained now the label yes. now I give this person the loan because that person is old enough, right? I don't know. Or I could change the income, 80K, Brooklyn, and not Harlem anymore. And now also we have the label yes. So we are granting the loan. So we have see here a situation in some sense similar to what we had with databases, right? By changing values here, I change the label. And I could say, I'm not going to develop this in detail, but in the papers, and actually in the presentation, I developed this idea a bit more. Basically, we can see in this case, the age is a counterfactual cost. In the sense, it's good enough to change this value to change the label. In this case, I need to change two things. So the responsibility intuitively could be 1/2 for each of them. Right, but that here in this case it's very important to realize that maybe this is still intervention is better than this one, because people call this kind of intervention something like actual or actionable explanation, in the sense that I can think that I can move, I mean, increase a bit my salary and move to a different neighborhood and get the loan, but changing suddenly from 18 to 25, my age, is not feasible, not doable, right? So maybe this one is actionable. And actually, in the context of reasoning with explanation, you can specify what is actionable and what is not. I have done that in some of the papers. Yeah. So this idea works very fine when we have binary features. Notice that this is not the case because we have a lot of possible neighborhood, and then you have to take into account that maybe with this particular change you changed it to yes, but any other neighborhood among 200, I mean, may not change the label. So that has to be taken into account, and it has to be a bit more subtle than this. And this, we have done that in a paper with Dan Suchu, Max Schleich, Fula Vagena. That's it, I think. Yeah. So the references are somewhere. So I'm going to skip this because I'm making Benny nervous here. Let's go back to Shapley value. Okay. Okay, just to make a coherent thing, right? I mean, feature values, how do they appear here? This is nice. Give me a few more minutes. I mean, I started at 11:15, right? Yeah, but then it's rushing. Okay, Shapley value. Feature values can be seen again. Shapley value. Now I'm not talking about causes in databases. The feature values are the players. The feature values in an entity. Yeah. Or the features. I mean, if we fix the entity, we talk about the features, not the feature value, because obviously you can get the values from the entity and the set of features, right? As variables, as functions. Yeah. So feature values can be seen as players in a coalition game, each of them contributing to a shared wealth function. So, and the Shapley value is an established measure, as I said before. So let's try to use it, yeah, directly in this case, in this situation. It is important to realize, because many people may have never seen it, this Shapley value emerges as the only measure that enjoys certain desired properties, as stated by Lloyd Shapley in the 50s, right? They're quite natural, and Lloyd proved that there is only one measure that satisfies those actions, those properties. So it's not something that we took from our pocket and let's play with this. I mean, there is something behind, underneath, that makes this relevant. Right? What is important, right? So we can safely use this. Of course, there are alternatives I have mentioned before, but trying the Shapley value is natural, right? Trying out. So for each game, the important thing is to define the appropriate wealth function or gain function, right? So let's assume for simplicity that we have a classifier that is binary. The labels are 0 and 1. That doesn't have to be like that. The set of players contain now the features. Since they are all relative to the entity at hand, basically we are talking implicitly about the feature values. And now the gain function, yeah, okay. The gain function is as follows. Well, consider this. We have the E is the entity at hand. ES is the projection of the entity on this set S of features. It's a set of features. So basically, I am fixing the values for those features as those that I find in the entity at hand. And then for the other features outside S, I allow them to vary, to change, to take all the possible values in their domains. When I do that, of course, each entity that I obtain this way, E prime S, that coincide on S with E, but not necessarily on the other features for the other, I'm going to get different labels when I classify this by means of a classifier like the black box that the bank had, right? And then I'm going to get labels, zeros and ones, and then I compute the expected label. Yeah, it's a number. It's a value between 0 and 1. Yeah. So this is the gain function. Yeah. And then, of course, I have to plug in this particular gain function into the general formula for the Shapley value. So this is what I get. The same as before. Now the subsets are subset of the set of features minus F star, that is the one I am concentrated on, the one for which I want to find, right, a score, right? And then the rest as before, the permutation, the number of permutations, and here is the difference between having F star and not having a star. Basically, it's a difference of 2 expected values, right? Over all the possible labels that I can get by making the feature values outside S and F, in this case, they take all the possible values in their domains. Yeah. So this is going to give me a number. Yeah. I already settled this. Okay. Why this? Well, this is a particular instantiation of the Shapley value that is a SHAP score that has become quite popular. It was introduced by Lee and Lundberg in 2017. And actually, there you will find plenty of papers, I mean, related to SHAP score. Yeah. Of course, it assumes a probability distribution because we are talking about unexpected values. As with responsibility that I mentioned before, without developing the details, you have to consider exponentially many combinations in the definition. But that doesn't prevent you from trying to find, for some cases at least, a way of computing this Shapley value, I mean, efficiently. Yeah. So this is a situation. In general, it's difficult, Sharpie, hard. Then, but now what happens in this? We have a situation like this. I have a black box originally in the here. It could be a black box. All I need to do is have a classifier and obtain values zeros or one. But what if I have a decision tree, something like this? My classification model is explicit. It's there. Can we do better than having just a black box classifier? What if the decision tree is, if we have a decision tree or a random forest that is related to the collection of decision trees, or a Boolean circuit? Yeah, Boolean circuit is also a binary classifier. Can we compute a SHAP in polynomial time? And we investigated this problem in details in the AAAI paper this year, and we identified tractable and intractable cases. And we provide the algorithm for the former, for the tractable cases. And in particular, we obtained that this can be done, it is tractable for decision trees and random forests, something that was something like a conjecture in the community. Actually, Lundberg and the co-authors, they claim they had proved this, but I mean, nobody I know has been able to understand the proof. So basically, we took it as a conjecture. Okay. Okay, so what is a Boolean circuit? I mean, very quickly, we have basically, let me go directly to this. This is a Boolean circuit. The inputs are these gates, x1 up to x4. These are the values zeros and 1. And then I propagate the values to the circuit as in propositional logic, and I get at the end a value 0 or 1. Yeah. And then I'm going to concentrate on a particular kind of circuits, basically those that are deterministic. The definition is here, but it's very easy to explain in this term here. The circuit is deterministic if every OR gate, here I have an OR gate, acts as an exclusive OR. That is the idea. Yeah? Act as an exclusive OR. Yeah. And then I'm going to be interested in circuits that are deterministic and also decomposable. What does decomposable mean? it is basically also can be shown here. Basically, for AND gates, like the one here, the set of variables that participate from this side is disjoint from the set of variables that are used from the other side, at the other side. Yeah. So basically, you have this joint set of variables, and these gates act as OR gates. Yeah. So you can say, well, why are we interested in these kind of circuits that are decomposable and deterministic in this particular context? Well, the issue is that several Boolean models can be translated in polynomial time into this class of circuits, which is good. In particular, decision trees, ordinary binary decision diagrams. I'm going to mention later on why they become important, and several others, but these are particularly interesting. Yeah. So basically, if you want to compile a binary decision tree into a Boolean circuit, basically you do something like an inductive construction. Here in this case, what I'm trying to suggest, I have this node N5. N5, this piece here, this is the decision tree. Yeah, zeros and one here at the leaves. This one is transformed into this circuit, and then I can continue doing the same with the other one, and by composition of these mini circuits, I produce the global circuit, and the final circuit is going to be the one for the top node over here. So basically, you can deal with decision trees through this class of circuits. Yeah, and this is computable in polynomial time. So we can basically if we obtain something good for DD circuits, we can have something good for decision trees. And actually, similarly for the order binary decision diagrams. Well, the theorem is that CHAP can be computed in polynomial time for this class of circuits under the uniform distribution. Yeah, this is the main theorem. We can compute the CHAP value efficiently under the uniform distribution. As a corollary, you get the same for decision trees, random forest, OBDDs. Under the uniform distribution, actually, it is possible to extend the result to any product distribution, and the uniform distribution is a particular case. Yeah. Order binary decision diagrams very quickly. What I have is something like this. Here I have a decision tree. It could be represented as an order binary decision diagram, like this. Basically, what is relevant to mention here, always you get 0 and 1 to classify something. What is important in this class of circuits is that every path of this kind follows the same order. Yeah. So here you have x1, x2, here x1, x2, x3. You shouldn't find another path where the order is permuted here, right? That is the. Why are these particular decision diagrams important? Well, for many reasons. They are heavily used in knowledge compilation, an area, useful, interesting area of AI, and also because it is possible today, in these days, represent opaque classifier, almost black box classifier, like binary neural networks and others, as OBDDs. And there is recent work by the group around Adnan Darvish that has been doing this, using OBDDs to represent things like neural networks. So you can apply basically the result that we have to those cases via this transformation. So that's why I'm mentioning this. I'm not going to give the idea of the proof. I mean, actually, you can find them in the slides. I'm going to leave for you. But the result usually basically uses the decomposition and the deterministic component to obtain the result. Well, you decide. I thought I had a few more minutes, but I mean, if you want to stop here, we can leave things for the. Maybe let me finish with the final slides I have. Is that okay?
Yeah.
And then I can show this if that is interested in the most recent problem which I have been working on has to do with reasoning with explanations using answer programming. These are, let me give you final remarks. So I think there are many interesting open problems in this area, full of open problems, many things to do. It's very exciting to be in this area. We have investigated complexity and algorithmic aspect of responsibility. The question is, what if we have the classifier, right? That was, I mentioned on that. I mean, but for this responsibility in particular, we haven't done much. Yeah, we have this for Shapley value, but not for responsibility. Yeah, so this is open in some sense. This is for me is a very important problem. The addition of semantic and domain knowledge, I think, is particularly important. I mean, these scores, as they are formulated, they don't take those elements into account. So how are we going to redefine the scores at the light of domain knowledge? Are we going to hack the computation, right, by somehow introducing the constraints or the semantic knowledge? Or are we going to change the underlying probability distribution? I mean, there are different ways to go. I have been working a bit on this, but yeah, but a lot needs to be done. Reasoning about counterfactual, that is the part I skipped from the slides I had. Also, I think it's very interesting to connect whatever we are doing in this area with model-based diagnosis. That is an older area of AI that has to do well, providing causes explanation for things that happen. And I'm also doing a bit in that direction. I think it's a very important problem because people talk about a model being interpretable or explainable, and they tend to use these two terms interchangeable. But I don't think they are the same. And actually, I don't even think that the people understand exactly what they are talking about when they talk about explanation and interpretations. So what is a good explanation? I mean, what is a good score? Well, we use a Shapley value that is a good score in game theory, but maybe for explanation in this kind of situation, we may find a different set of principles that lead possibly to a different score. I think this has not been properly investigated yet. Okay, another important point, explanations are at the base of fairness and bias analysis, right? For example, identifying unexpected or undecidable high score features becomes relevant. I mean, if I notice that I am deciding on the base of race or whatever, I mean, maybe there is something I can do about that, right? So, but possibly it's not going to be enough. I mean, we need more in the direction of fairness and bias analysis. Also understanding the decision in relation to what have been called protected features becomes relevant here. And that's something that should be formalized and automated and so on. So we have to explain how decisions are made. For example, you have a situation here, decision tree, for example. Here we have two entities that are going perfectly well along the same path, and suddenly at the level of race, they depart. I mean, the one goes into yes, the other one's into no. Well, we should be able to identify the situation. We should be able to query these situations. And some of my colleagues here in Chile have been working on this, but I think this is a very interesting area in which more research is needed, right? I think this is also a very important problem, high order analytics on explanations. Maybe we can leave that for the discussion or the question and answer part. But I mean, what if you have plenty of explanations? Well, what can you do with that? Can you learn something about, I mean, the classifier? Can you learn something about your population? I mean, that has not been addressed as far as I know. So what else can we learn about the population or our classification mechanism? Right, so there are many interesting issues too. Here, as I said, I have all the reference that in which I have participated with co-authors in case you want to go into the details. And so that is what I wanted to say then. Yeah, so.
Great. Leo, thank you very much. This was a beautiful tutorial.
Thanks a lot for giving me the opportunity to present a few things in which I have been working and I have been interested as well. There is a lot of many things to do, and it's a promising area, research area.
Yeah, these are some of the things that we wanted to ask. So originally the plan was to have an interview for like 20 minutes, but with this delay, we'll change a bit, I guess, the plan, and just maybe ask a few questions for a few minutes, maybe just the burning ones. So Vanina, do you want to ask?
Sure.
Yeah, the plan is that Vanina and myself will do the interview, but again, we'll shift the plan a bit.
Hi, everybody. Can you hear me?
We can hear you.
Hi, Leo. Very nice talk.
Hola, Vanina. Hi, Vanina. Nice
¿Cómo
to see
estás?
you. Thanks.
Okay, so one question that I have about this work that I think it's really great that you've been able to combine this two interesting topics together, like within AI and databases and this boom on explanations. But one question that I have is, and you have experience with this, is how is the industry taking this kind of approaches? Are they actually do they want to include this kind of frameworks in their developments? Is it hard from your point of view to engage them to use this?
I don't think, yeah, I think that's a good question, very good question. Well, I can say a couple of things. I mean, first of all, I mean, I think attribution scores are being adopted by industry. I mean, actually, there are implementations in real commercial and use systems. So one example that comes to my mind is data robot, for example, that is actually relatively widely used. And actually, when I was talking before about these higher level explanations, I mean, actually that came out of a discussion conversation with one of the guys at Data Robot that he has been collecting, I mean, plenty of explanation, and then whatever analysis that he does is usually by hand. It's usually nothing systematic. But they are able, through Data Robot, for example, to compute SHAP scores. I didn't know that. I mean, so I think this is very interesting. I have a student of mine. I asked him to look into this in more detail. So we are trying to collaborate with them. So, okay, the answer is yes, there are implementation commercial systems that do compute SHAP score. I mean, and also I would like to mention relational AI. The work I did with Max Schleich, Dan Suciu, and Fula Wagena started at Relational AI, the startup where I met, well, not exactly there, but I met Benny for the first time, the predecessor, Logic Block. Yeah, they is a very interesting company. They are doing things at the frontier of research and development. That is, and they are very much interested in the subject. And I started working this subject in the context of that startup, right, with Suciu, Schleich. And actually Max and Dan Schleich and Dan Suciu, they keep doing research in this area with the support and interest from relational AI. So Max Schleich is being, well, paid by relational AI, and they are working in this area. So, and also I have seen a lot of applied work in the direction of machine learning and explanation in medical domains, for example. So I think this area is here to stay. I mean, and it's being adopted. I mean, so by companies, industry, and applied data scientists. Yeah.
So, Leo, I had this comment, Andreas. I see that you're raising your hand. I'll let you speak there.
Okay.
Just one small comment and then a question. You said, Leo, that you talked about the fact that we've been looking at these problems of explanations, but they're kind of formulations of things that we've been looking at in the past, like the repairs. And another example that you didn't mention is that of view updates, deletion propagation, where we were.
Yeah, you're right. You have done work on that.
Exactly. We've been looking at, what is the minimum number of tuples that you need to remove in order to make some query answer false. So it really seems like we've been looking at these problems, but we didn't view them as really as explanations or responsibility.
Let me say, I don't know. I think I should say something about this. So something I was planning to present in this paper, this presentation, I mean, not today, I deleted it yesterday anyway, was about the causality in the presence of integrity constraints. Yeah, integrity constraints are views. They are companion, right? I mean, so you can move from views to constraints or the other way around. And actually, we proved in a paper with Babak Salini that if you introduce integrity constraint, the responsibility computation, they can go higher in complexity. And actually, we use to obtain the result your work on on view updates, right?
Yeah.
So that here there are very interesting connections that maybe, I mean, they are fascinating, and you can borrow results from one area to
Right.
apply them on the other. So your work on view updates was crucial for obtaining complexity and algorithmic results for causality under constraints. And I emphasize, for me, all this makes sense in the presence of semantic knowledge, domain knowledge, and that is something that the community have been neglecting in my view. So I'm trying to contribute in that direction.
So I wonder, in terms of open problems, it seems that like you didn't talk about non-answers. Like, why didn't I get this answer? And the original work of Suchu and Meliu and Gattabauer, they did look at the non-answers. Do you see the connection? Do you see, is there like things like Shapley value, Banzaf, and so on, are they relevant to these like negative questions?
To be sincere, I know what you are referring to. I mean, I have seen those works. I haven't worked on negative answers. So my feeling is, first, that there should be a way to apply them. And also think that it will be a very interesting problem. I mean, how to apply these scores in the context of no answers. Obviously, you have to reformulate the problem, but maybe a sort of reduction is possible, right? But I think that's a very interesting research problem, but I haven't seen anything done in that direction. But that's a very interesting problem to address. I cannot say more than that. I haven't worked on negative answers. I mean,
me too.
I mean, one has limited time and limited company as well.
Andreas, do you want to ask a question?
Yes. Yeah, I would like to. Let me turn on. Okay, yeah, I'm here. Good.
Hi, Andrea. Nice to see you.
Yeah, good to see you guys after 2 years. It's unbelievable.
Andreas, hi.
Hopefully we'll meet soon, and have a beer or something.
Yeah.
So actually, yeah, this is something that I asked Leo some time ago. I don't know if Leo remembers that, but
I have Alzheimer. I have
but and I wanted to ask this again. Maybe the last couple of years something else popped up. So it's about okay. So you're trying to measure the contribution of an atom to query results, and that's a very natural thing to do, and that's where the Shapley value comes in. But for me, it's equally natural to ask what is the contribution of a set of atoms collectively to query results. So if we cast this as I mean, in this game theoretic context, it's like computing the Shapley value of a group of players instead of a single player. So so this is what we discussed some time ago. I think this was POTS in Amsterdam, I believe. So it seems that there are several definitions out there computing the Shapley value of a group of players. But it seems that these are not, there is no consensus which is the right definition, or I mean, they behave differently. And so my question then is that, I mean, have you thought how we can measure the contribution of a set of atoms to query results, or using ideas coming from game theory? So that's what I'm interested in. And I just wanted to ask whether you thought about that, or
I mean, I have thought about that mostly from the point of view of the relevance of doing that. And from the purely technical point of view, I realized there is some work, I mean, on let's say Shapley values for a group of players. I think they call in some papers cohorts. Actually, there will be next week a presentation from someone from Stanford about that. I will send you the link in case you're interested, because I'm planning to attend.
That would be good. Yeah.
Exactly on that. But so I think that is relevant. I haven't worked myself on that, but let me say why I think it is very important. For example, I see that in concrete application. For example, I would like to tell someone, well, maybe that person wouldn't like to hear that, but maybe I might want to tell someone, well, you know, I'm not giving you the loan because of your socioeconomic situation, right? That is not relative to a particular feature like the salary, or it's basically something like a category, right? So I really want to think at the higher levels in terms of scores and even causality. Yeah, I think higher level causality and scores are crucial. Right? That is usually how people understand things better. I think in terms of categories of feature values or possibly categories of tuples. I don't know. And so I would start. I mean, actually, I propose a student of mine to start looking into causality scores in the context of, for example, multidimensional databases where you have abstraction, you have higher level categories, right? So, well, something similar, I think, should be done in the context of explanation for classification, categorizing features in groups that are relevant, right? I mean, maybe it has to do with, I don't know, geographic situation, but it's not represented by one single feature, by the group of features and so on. I think that is really important for interpreting these results as well. Yeah. And this also touches another point that I think is fundamental. Let me stop me, Benny, if you want. But I think it's very important as well. I mean, we have to make all these explanations, I mean, understandable, I mean, accessible to the final user, right? So what is a final user going to do with a number? I mean, actually, I really want to try to take seriously the idea of interpretation. And what is interpretation for me? For me, interpretation is what it is in logic, right? It's a mapping into a set theoretic structure or into some sort of symbolic alternative or like an ontology, right? I mean, so it should be expressed in terms of something the user can understand, can make sense of, and usually that requires some sort of abstraction, right? Categorization. So I think all these things are related, are connected, and have practical impact, yeah, or should have, right? I don't know. I mean,
I think that it sounds like relating to this difference between the so-called local explanations and global explanations.
Yeah,
like local explanation is why did I get a particular answer, a particular classification, a particular instance, and global explanation is what is this model doing? What is this complex neural network doing in simple, approximate terms and so on? So it seems to be related to that.
Yeah, definitely. Yeah, actually, I don't think people really understand what they are talking about when they talk about explanations or interpretation, first of all. However, having said that, I think they still understand better things at the local level. But what does it really mean to understand a whole system? I mean, it's very difficult to tackle that question, right? I mean, unless you have some sort of interpretation in these more formal terms. I mean, right? I mean, you understand things when you map things into another, right? I mean, and you are more familiar with the other one. Yeah, but and I think that has not been systematically. This idea has been not systematically developed. So, for example, I mean, I will understand the system if you map them into an ontology, for example. I can understand or something like that. But I don't know.
So there is a lot of work nowadays. Please, Benny.
No, I'm just saying that we need to finish because the plan was to finish
okay, that's fine.
20 minutes ago, and we have the discussion room after the break, so we can get in and address you and I.
We can continue this discussion.
Yeah, good questions for this discussion. So, so is it okay? Andreas,
absolutely, absolutely.
And then we'll continue in the discussion.
Yeah, of course.
So let us take 20 minutes of a break, and then we return to this room, right, Renzo?
Yeah, that's true. 20 minutes. It's good.
Right. Very good. Okay. Thank you again, Leo, for the wonderful presentation and great tutorial.
Thanks to you for the invitation again. I'm happy to be here. I see so many people. I mean, I hope we will
Pleasure.
keep our community alive, so we should meet in person as soon as possible. So, and friends,
Don't go away, Leo. We want you in the room, in the other room.
Yeah, but we can take a break.
okay, yeah, but yeah, maybe you will explain how we resume after the breakout.
Just,
Or?
just the same link, and then within Zoom we'll break out rooms, so you can go to the ones we.
I have no idea how to do that. I have no idea how to do that.
Oh, no, Renzo will take care
Quite
of that.
easy,
Just
quite
go into
easy.
the-
Don't worry. It's the same link.
Yeah, okay. Let's see you. Okay, 20 minutes break then. Okay.
Yes.
Okay.
Thank you.
Back to you.